Hello, Chem 100. We are starting Chapter 2, which is Chemistry and Measurements. So get your notes and let's get started. This chapter's career focus is on the registered nurse. An RN promotes patient health, prevents and treats diseases. They help patients cope with illness. They calculate drug dosages, and they maintain medical records of patients' symptoms and prescribe medications. Section 1 in this chapter is looking at units of measurement. And we are going to write the names and abbreviations for the metric and SI units used in measuring volume, length, mass, temperature, and time. This should all be in your notes. For example, we can write something as 1.7 meters or 65 inches. Label the mass of something as 58 kilograms or 128 pounds. The distance of something is 2.1 kilometers or 1.3 miles. This is our metric. This is our English unit. 12 kilograms or 26 pounds, again metric in English, and temperature 22 degrees Celsius and 72 degrees Fahrenheit. Chemists use the metric system and the International System of Units, or SI System International, for measurements when they measure quantities and they do experiments and they solve problems. We are used to using the English system because we measure things in inches, feet, pounds, miles, but chemists and other scientists use the metric system and the SI system to be able to communicate with scientists around the world. Here are some units of measurements and their abbreviations. For volume, the metric system uses the liter. SI uses the cubic meter, easily to convert from one to the other for all of these. For length, it's common to just use the meter for both of them. For mass, we use the gram in our metric or kilogram in our SI units. Temperature, Celsius, and SI is Kelvin, easy to convert from Celsius to Kelvin. And time, again, just like the meter, is seconds for both of them. Let's look at volume. Volume is the space occupied by a substance. It's measured in cubic meters in the SI system. It's commonly measured in liters and milliliters by chemists. We can see here if I've got a liquid filled in this graduated cylinder, we can measure by looking at the meniscus. We need to figure out what those little increment measurements are to measure the volume. Some useful relationships between units. 1 liter is equal to 1,000 milliliters. 1 liter is also equal to 1.057 quarts. So then we could say that 1 quart is equal to 946.4 milliliters. Knowing these two, we can make this assumption. The length of something is measured in units of meters in both the metric and SI systems. We also can get from meters to centimeters. A lot of us are used to using yardsticks, but the meter is slightly longer than a yard. Some useful relationships. 1 meter is 100 centimeters. 1 meter is also 1.094 yards. So we can then say 1 meter is 39.37 inches. We also know that 1 inch is 2.54 centimeters. These are all relationships with length. The mass of an object is a measure of the quantity of material that it contains. It's measured on an electronic balance such as this. It has the SI unit of the kilogram. However, in lab, our scale will be set to grams, which is the metric system. And like it says right here, we will use grams on our scale. We can easily convert from grams to kilograms. That will be in a different lesson, but you're going to see how easy it is to convert from one unit to another. Here's some useful relationships between units of mass. 1,000 grams are in 1 kilogram. 1 kilogram is also equal to 2.205 pounds. So this is our relationship from metric to English. This is a metric and a metric measurement. We can then say, if we know how many grams, we could say 1,000 grams is equal to 2.205 pounds. If we were to divide both sides by 2.205, we would find that 1 pound is equal to 453.6 grams. Now, you might be more familiar with the term weight over mass. Weight is the measure of the gravitational pull on an object. If you were to measure your weight on Earth and then your weight on the moon, it would be drastically different. So scientists measure mass rather than weight because mass is not dependent on gravity. Looking at the temperature of something, the temperature is a measure of how hot or cold an object feels. We measure that on the Celsius scale in the metric system, which we then can convert into the Kelvin scale. 18 degrees Celsius, 64 degrees Fahrenheit. We can see on this scale that on the left is our Celsius and on the right is our Fahrenheit. In a different lesson, we'll see how we can convert from one to the other. Time is based on an atomic clock that is measured in units of seconds in both the metric and SI system. We know that in one day there's 24 hours in a day. We know that in 1 hour there's 60 minutes, and in 1 minute there's 60 seconds. We could figure out how many seconds there are in one day. If there's 60 seconds in 1 minute, and 60 minutes in 1 hour, and 24 hours in one day, we could easily do this math to figure out how many seconds was equal to 1 day. Let's do a sample problem. On a typical day, a nurse encounters several situations involving measurement. State the name and type of measurement indicated by the units in each of the following. If a patient has a temperature of 38.5 degrees Celsius, a physician orders 1.5 grams of medicine for an injection. A physician orders 1 liter of a sodium chloride solution to be given intravenously, and a medication is given to a patient every 4 hours. Can you tell me what type of measurement those units are? And hopefully you said that degrees Celsius is a unit of temperature, a gram is a unit of mass, a liter is a unit of volume, and an hour is a unit of time. Check over the learning goals to make sure that you understand this section. Section 2 is about measuring numbers and significant figures. You're going to be able to identify a number as measured or exact and determine the number of significant figures in a measured number. A measuring tool is used to determine a quantity, such as the length or the mass of an object. A measuring tool provides numbers for a measurement, called measured numbers. To report the length of an object, we observe the numerical values of the marked lines. This is super important. We have to look at the marked lines on our tool, and I'm going to show you a picture on the next page. We estimate the last digit by visually dividing the space between the smallest marked lines. That estimated number is the final digit that is reported for a measured number. For example, if I look at my tool, here is my tool. My tool has markings on it. And these markings tell me that they are whole centimeters, 1 centimeter, 2 centimeter, 3 centimeters. So if I'm looking at this piece of wood right here, it's not 4 centimeters, but it's not 5 centimeters. The next digit that we can estimate after a whole number, if this is my whole number, the next digit to the right of a whole number is to the tenths position. So we would estimate. Now you might estimate and say, well, that's 4.4 centimeters. That's okay. You might estimate that it's 4.5 centimeters. Maybe you look at it and go, it's 4.6. I don't know if I would go that high. It looks to be pretty much right in between the two. But that tenth of a digit is the estimated value. That's what you need to report to because of this tool. The markings on this one, I would say, okay, the numbers are 0, 1. These are whole numbers, but there's little tick marks in between. How many tick marks? If I counted, there would be 10. So this tool can measure to the tenths. What digit is 1 past the tenths? Well, 1 past the tenths would be the hundredths position. We need to estimate. We can be exact to the tenths. So I would say this is 4.1, 4.2, 4.3, 4.4, 4.5. It's after 4.5. We know it's at least 4.5, but it's not 4.6. So we would estimate after 4.5, sure, let's put a 5. Maybe you said 4.56. Maybe you said 4.54. That's okay. This last digit that we report is an estimated digit. But using this tool, we need to estimate to the hundredths because my tool can be exact to the tenths. Now let's look at this. This brick is right on that 3. So it would be very easy to say it's 3 centimeters. But remember, we said, if my tool allows me to be exact to the whole number, which that's what these markings are, they're whole numbers. There's a 4 tick mark, there's a 5 tick mark. There's nothing in between. If I can be exact to the whole number, I need to estimate to the tenths. So in this case, if you think it's right on that line, cool. You would say 3.0. Maybe you would look at this and go, oh, I think it's slightly over. Maybe it's 3.1. Maybe you would look at this and say 2.9, but if you say, no, that is right on that 3, then you better say 3.0 because you can estimate to the tenths on this tool. In a measured number, the significant figures are all the digits, including the estimated digit. all non-zero numbers. That means everything that's not 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Anytime you see any of these numbers, they are always significant. Zeros may or may not be significant depending on where those zeros are. We'll talk more about those significant figures. Let's look at some rules. A number is significant if it is a non-zero digit. Here's an example. 4.5 would be 2 sig figs. 122.35 meters, all of those numbers are significant. That would be 5 significant figures. A number is significant if a 0 is sandwiched between two non-zeros. So if there's 205, that 0 is sandwiched in between two numbers, so it is significant. That would be 3 sig figs here. 5.008, those two zeros are sandwiched in between the 5 and the 8. So all of them are significant. 4 significant figures, all of those numbers. If a 0 is at the end of a decimal number, now here is a decimal that they made sure to tell us that it's 50 point liters. They didn't want you to go, it was about 50. No, they said 50 on the dot. So that would be 2 significant figures. 16.00, those zeros that are after the decimal point are significant. So this would be 4 significant figures. Everything written in scientific notation is significant. 2 sig figs, 3 sig figs. Now here's when zeros are not significant. When it's at the beginning of a decimal number. All of these zeros before that 4 are not important. There's only 1 significant figure in that number. Now if there was a number but right here like 10.0004, then all of a sudden those zeros are sandwiched and those zeros become important. But it's not just as is written. 0.075, those zeros are not significant. It's just 2 significant figures. Zeros are also not important when it's used as a placeholder in a large number without a decimal point. So 850,000 meters, notice there is no decimal point, so we do not count those zeros. We only count the 8 and the 5, 2 significant figures. This 1,250,000 grams, only the 1, the 2, and the 5 are significant. Those zeros are just hold in place. 3 significant figures. Let's look at these examples. 3815, those are all non-zeros, 4 significant figures. 2 significant figures. 3 significant figures. Count all those, that would be 5 significant figures. Again, when they're non-zero numbers, we count them all. These ones get a little bit trickier. 50.80, that 0 is sandwiched, it is important. This 0 is to the right of the decimal, it is important. We count all of them. This is wrong. This should be 4 significant figures. 2001. The 2 and the 1 are obviously significant. Those 2 in between are sandwiched. 4 significant figures. The leading zeros are not significant figures. Just the 702. That 0 is sandwiched. So 3 sig figs here. And this 0 is not significant. Everything else is. Those 2 zeros there are sandwiched. So 1, 2, 3, 4, 5. Zeros at the end of decimal numbers are significant. Yes, yes, yes. All these zeros. So 4, 3, and 4. Here are some examples where the zeros at the beginning of the decimal point are not significant. This is not significant. Those are not significant. These are not significant. Let's see though. Is this 0 significant? Yes. It's after the number to the right of a decimal. So this would be 3 sig figs. Those 2 2s are significant, and the 3, 6, and 1 are significant. Zeros used as placeholders in a large number are not significant. 44,000 only has 2 significant figures. Just those 2 4s. Those zeros are not. However, when there is a decimal point specifically written at the end of a big number, 500 is still a big number. It's not 500 million or anything that big, but if there is a decimal point shown, then that is telling me that that is there for a reason, and all of those zeros are significant. So this would have 3 significant figures. Here's some examples of those zeros in scientific notation. Again, whenever something's in scientific notation, everything is significant. You just count everything. That would be 3, that's 2, and that would be 5. Keep only the significant zeros when writing numbers in scientific notation. If I said I had 500 point. Again, this was 3 significant figures, so if I write it in scientific notation, I would say 5.00. I need the 3 significant figures, and when we write it in scientific notation, it has to be a number between 1 and 10. So my decimal point would go right there to make it 5. but I need to include those zeros. 5.00 times 10 to the second grams. This only has one significant figure. All of these other zeros, no, and there's no decimal point. So we would just say 4 times 10 to the fifth. Only one significant figure. 3.00. This zero is not significant, but those zeros that are after the decimal are. So 3 significant figures. That means when we write it just like this guy up here, we have to include those 0.00 at the end. Exact numbers are numbers that are obtained by counting items or by definitions that compare two units in the same measuring system, like metric to metric. When I said 1 kilometer equals 1,000 meters, that is a definition comparing two units in the same measuring system. Exact numbers are not measured. They do not have a limited number of sig figs. They do not affect the number of significant figures in calculations. Here's some examples of counted items. If I counted that there were 8 donuts or 2 baseballs or 5 capsules. Here's some examples of those defined equalities. Like I said, 1 liter is 1,000 milliliters. 1 meter is 100 centimeters. 1 kilogram is 1,000 grams. Or if I'm using just the US system, 1 foot is 12 inches. 1 quart is 4 cups. 1 pound is 16 ounces. But you have to stay within the same system. Let's look at an example here. Identify each of the following numbers as measured or exact and give me the correct number of significant figures. Why don't you try and pause here? Let's see how you did. Step 1. A measured number is the result of a measurement. An exact number is obtained by counting or by definition. So A and C are both measured. A is a measurement of volume and C is a measurement of time. B and D are exact. B, we counted 4 knives. D is by definition that in 1 meter there's 100 centimeters. So let's look at this number of significant figures. A has 3 significant figures. That 0 does not count, it's leading. So 1, 2, 3. C has 2 significant figures. We count what's in the scientific notation. Measure numbers and significant figures review. Double check these learning goals and just make sure that you understand all of these and are able to do them yourself.